Yeah.
Okay, we're good?
Yeah, we're
okay,
good.
Don't hit the card, and we're good, right? Okay, good. So, let's talk a little bit about the material in chapter 21. This is kind of a bit of an overview. Heat is energy in transit. It's when it jumps from one substance to the other. It's before it's integrated into the substance. It's waste energy, and it's transferred because of a difference in temperature. Clear?
Yeah.
That's why it's transferred. Now, let's say that you have two substances. Okay, here's a piece of metal and my hand. I'm going to hold on to the metal. Now, the metal's cold. Would you agree?
Mm-hmm.
It's warming up. There'll become a time where my hand is warm and the metal is room temperature, correct? Plus it conducts heat, of course, but it's in an insulating handle, so if I put energy into the metal, it's not going anywhere. So what's going to happen? It's not like if I have a faucet that is connected to pipes that go into the ground, I could literally funnel energy through the pipes into the ground forever. It's going to be conducted through the pipes into the ground, correct? But here, this is on a handle. So this is going to absorb energy from my hand. That's the definition of cold. When my hand loses energy, it feels cold. It goes into the metal. Why? Because there's a difference in temperature. I'm 37 degrees-ish. This is 25 degrees-ish. So you're going to get that transfer because of a difference in temperature. And the transfer is going to take place until they're both the same temperature, until there's some kind of thermal equilibrium, correct? Between the two, you're going to get that transfer to take place, correct? Now, be careful with temperature. Temperature is not a measure of total kinetic energy. People will say that to you, but it's really not. It's really a measure, it's a proportional to the average kinetic energy of molecular transitional motion. Or simply put, it's an average. It's an average, it's proportional to an average kinetic energy, an average molecular kinetic energy. Okay, that's putting it a little bit more succinctly. Internal energy, you have to know what that is. That's the total sum of all the energies in a substance. We call that the internal energy. That's the total sum. Again, some of this is, you're looking at me, this is a little bit of a review. What else? Bomb calorimeter. How do I actually measure the amount of energy in food? I burn it using a bomb calorimeter. But let me talk to you a little bit about that. If I put food in a bomb calorimeter. Now, think of a giant bowling ball. That's the bomb, okay? Now, the engineering will make this work, so you gotta use a little bit of an imagination. Does anybody not know what a bowling ball is? You know, everybody knows what a bowling ball is, right? It's a sphere, it's round, solid, okay? Now, let's say, I'm going to erase some of this. We talked about energy in transit as heat. Okay? So let's say I take a bowling ball. Okay? Now that's three-dimensional. It only looks two, but it's three-dimensional. Yeah. In the volumetric center of that bowling ball, I put food. Okay? I put some kind of dry cereal, something dry. Okay? Right? Now, surrounding that cereal is water. Correct? It's water. You okay with that? Yes? Okay. Now, I somehow rig a spark, some kind of fuse, and I light that food so it burns. I somehow rig some kind of electrical something where it's going to give off a little spark of known energy, and that spark is going to burn the food's going to burn and be turned into ash. Clear? Now, as a result of that food burning, it's going to give off a lot of energy because it's going to burn, right? Yes? Now, this container is not at all insulated. So, all the energy goes from the food into the water. You okay with that? Yes or no?
Yes.
Okay. So, you can say that the heat gained by the water, plus the heat lost by the food is going to equal 0. Correct? Yes?
Yes.
So the heat gained plus the heat lost is going to equal 0. Easy? No problem with that?
Yeah, no.
I'm socially distancing here. I'm 3 meters. Okay? I'm okay?
Yeah, of course.
Okay. So, if I can measure the heat gained by the water, will I be able to determine the heat lost by the food? Can I? All right. So here's the magic equation. All right. Can I erase some of this?
Yes, sir.
Temperature is proportional to the average kinetic energy of molecular translational motion. What's translational motion? Just moving from here. Catch. That's ooh, glad I didn't hit the camera. That's translational, right? Moving from here to there, correct?
Yeah.
Okay. So, right? Yes? Okay, so the heat, this is heat, equals the mass of the material, right? Yes? Yes?
Yes.
Times the temperature change. This is going to be of the water, okay? Is that okay? Times C. We say constant pressure, 1 atmosphere, laboratory. That's what I always said, C. C is now, let me give you a definition, okay? Yeah, you all right with that? The specific heat capacity of a substance, write this down if you have to, it's on film, Whatever, you can look at it later. You ready? The specific heat capacity of a substance is the amount of heat needed to raise 1 gram of the substance 1 degree Celsius. That's the specific heat capacity. For water, it's 4.18 joules per gram degree Celsius. So it takes 4.18 joules to raise 1 gram of water 1 degree Celsius. Now, this is an intensive physical property, right? It's also, some books call it simply a characteristic physical property. I know that Kostov could say it much better. I know that. I apologize. So, inside joke. So, intensive physical property. So in other words, I can use the specific heat capacity of a substance to help me identify that substance. For instance, I happen to remember iron is about 0.45 joules per gram degree Celsius. Aluminum is about 0.93, I think. About. Right? Yes? Yes? About. So if I had an unknown metal and I measured its specific heat capacity, I could use that to help me identify the metal. Could, right? Yes? Okay. So, water is that. Water is that. Okay? So, can I erase some of this? So if I said to you, I have, in the bowling ball, I have 400 grams of water, right? Let's just say I have 400 grams of water. Is that right? Let's say the temperature went from 25 degrees Celsius to 28 degrees Celsius. That's an enormous jump, by the way, but let's just go with that. How much energy did the food lose? How much? How much? Well, it's going to be the amount of heat gained by the water, right, is going to equal the mass times the change in temperature times that. So in terms of joules, it's going to be 400 times 3 degrees Celsius times 4.18 joules per gram degrees Celsius. So what is 400? On your calculator, somebody do it for me. 400 times 3 times 4.18. What do we got?
400 times.
What is it?
400 times 3 times.
400 times 3 times 4.18. What do we got?
5,016.
Equals 5,000. 15?
16.
5,016 joules. Is that what you said?
Yes.
All right, so that's how many joules were in the food. Easy?
Yes.
Yes?
Yes.
Easy? Okay. let me show you something. Calorie and joules, calorie and joules, calories and joules, calories and joules. Okay? Yes?
Yes.
So I know that there are 4.18 joules equals 1 calorie. Notice I wrote small c. Right? I know it's weird. I know. Just bear with me for a second. So I could say here, I could say this. Instead of saying 4.18 grams, 4.18 joules per gram degree Celsius, I could say 1 calorie per gram degree Celsius. I can say that instead, right? So what's 4 times 3 times 1?
It's 12.
1,000 what?
4.
It would be 1,200, right? Right? Yes? 1,200?
Yeah.
So that food had 1,200 calories. Right now, I know, this is a little weird. You're going to want to go back and look at this tape again. 1 calorie, small c, right? 1 calorie, large c, equals 1,000 calories, small c. I know, it's so weird. Calories are weird. Capital C is dietary calorie. The dietary calorie. Understood? So that food was 1.200 dietary calories. Okay? So let's say it was a little cereal. A little cereal. Understood? It was a little cereal. So that gave off 1.2 dietary calories. So do you see how industry, the food industry, when they come up with calorie counts, if they want to do it correctly, they'll use a bomb calorimeter, find out how much energy was given off by burning the food indirectly by measuring how much energy was absorbed by the water, and then they can find out how much energy was burned by the food and convert it to calories. Do you get it? Do you get it?
Yes.
And that's it. That's it. That's how you determine the caloric value of food. And understanding this, 4.18 joules per calorie, understanding that 1 dietary calorie is 1,000 scientific calories, clear? Or 1 dietary calorie equals 4.18 kilojoules, right? It's 1,000, right? Because when I say this is scientific, right? So 1,000 scientific joules is a kilojoule. 1,000 scientific calories is 1 dietary calorie. You get it? You sure? All right, easy? We'll go over it again. The last thing I want to show you is there's another type of, can you maybe turn the camera here?